because I think he was getting like
hate mail or something?
yeah, hate mail, and he just couldn't handle it anymore.
He didn't appreciate what other people were saying about how it destroyed them. I saw a review of it once online. It was like this long. It was incredible. It was pretty funny.
Yeah, why would you?
It was a funny review.
Why would you put your whole life
About how he loves it, but it's destroying his life. And, like, got a divorce.
And he's using more time to write about it too. So
people are just
it'll destroy your family.
Thinking out loud, yes. Just thinking out loud.
oh no, Floppy Boys destroyed my family.
When I read that, I was like,
Okay,
you know what? I think I'll check
wait,
it.
hold on a second here. Okay, it's destroying my life again.
oh no.
All right, so let's go ahead and take a look at this little article first. Okay, you know, 3 names that you usually do not mention in the same breath. Okay, Elmo, Captain Kirk, and Linux. Okay, I'm not sure how many of these 3 terms that you are familiar with. Elmo from Sesame Street. Okay, James Kirk from Star Trek. And Linux, you know, it's Linux. It's what I'm using right now. So the only thing that can tie these 3 names together is in this picture. It is it's a destroyer. It's a new destroyer class. You know, the Zumwalt. The first one, the Zumwalt was the first of the 3. There will only be 3 made, okay, because of it being expensive. And I'm pretty sure there are political reasons for it and whatnot, but there will only be 3 of these destroyers ever made. And they are not really, I don't think they're truly intended for combat situations, even though it is combat ready, but it's more of a test bed or test platform for technologies to come. So how can this thing tie all the other items, the 3 words that I mentioned, or the 3 phrases that I mentioned together? First of all, this is the USS Zumwalt, okay? And it's named after an admiral. And guess what is the first name of that admiral?
Elmo.
Elmo, exactly. So there goes Elmo. Okay. Second one. Okay, you look at that bridge of this ship here, this part here. It's actually pretty sizable. And there are different ways to describe it. There are Navy ways to describe it, but to us, computer geeks, it's a floating data center. And guess what type of operating system they use in the data center?
Linux.
Well, there goes Linux, right? So we only have Captain Kirk left. Okay, well, I'm guessing by now you should probably know, how Captain Kirk would fit into this picture.
He's the actual captain.
He is the actual captain of this ship, okay? It's James A. Kirk, not James T. Kirk. And I'm pretty sure, it was not coincidental that the Navy, actually had a sense of humor and just decided, let's throw things together in a kind of interesting way. But the interesting part about this is Raytheon was the contractor who developed the software of this thing. And from the complexity of something like this, I would imagine they had to hire quite a few developers or dedicate a few developers just on this particular project. Before the ship was launched, the software system was already revised a few times, big time revisions. The control room of this ship looks more like the Enterprise, the new Enterprise in the Next Generation, than the old Enterprise in the original Star Trek. In the old Enterprise, all the stations are fixed. Okay, Spock is only at one spot, right? Zulu is always at one spot because everything was hardwired back then. This is more like the new Enterprise, where the console, you can transfer control from any console to any other console. Okay, so that's kind of cool because the captain can be in the bathroom and still be commanding the ship.
Yeah, but that's not true for all the consoles. There's only going to be certain consoles that are going to be interchangeable.
Right, but in theory, because it's all networked, it is, you can even remote in if you want to, right? I mean, the captain can be, on vacation and still be, driving the ship around.
I wouldn't trust that cousin.
But that's where we are now. I mean, the whole thing is so computerized. Most of the systems, the engine, the weapon systems, and and stuff like that, they are fully automated already. Okay, in other words, it needs a smaller crew, than other warships because a lot of the stuff is already fully automated. So it's kind of interesting, and also the fact that they picked Linux as the operating system of the systems on this ship is also kind of interesting because most people do not think that the DoD would use Linux, which is open source, because open to many people means insecure, right? I mean, if you just listen to the term open, it's like open, right? I mean, it's open to attacks and whatnot, but the truth is when it's open, it's also open for auditing. Okay, in other words, if you have the source code of an operating system, it makes it easy for people to go through the operating system in the source code line by line to see if there are potential problems. With Windows, which is a proprietary type of software, you don't know. I mean, unless you ask Microsoft, and say, okay, release your source code so we can go over that source code and look for problems. What are the chances that Microsoft would say, yeah, I kind of like you guys doing free work for me, so go ahead, check my code for problems. What are the chances of that happening? Do you think even the government can make Microsoft release their source code?
No.
Probably not. Okay.
Not that good reason.
Exactly. And this is the other one. It's still related to the government, the federal government at that. The TSA still uses Windows 98 and Windows 98 and Windows XP on their X-ray machines. The X-ray machines at the airport, where they make you check your bag and they want to look for suspicious items, those things are still running on Windows 98 and Windows XP. And some security experts have found a way to quote-unquote hack into those things so they can inject images on top of the actual image being items scanned through. But the good thing is those machines are so old that none is Wi-Fi enabled. So they're not networked at all. In order for any hacking to be done, it has to be done right there in person.
Kind of awkward.
Yeah.
You
Well,
just sitting
it's-
there plugged into the X-ray machine. How you doing?
It's like, hey, can I just plug this in here?
Well, you just pull up a polo shirt with Microsoft logo on it, and you just walk up to it and say, "I'm performing a system update. It needs Surface Pack 20, right?"
It's only on 4, man. This thing really needs upgrade.
Then again, if people can have that kind of access, to airport security, we have a lot of other things to worry about.
Certainly not on the top of the list.
Maybe these are just decoys. Yep.
Most state agencies are still on 98 or
I would say XP. 98 is really, really ancient by today's standard.
yeah, XP. I think
Yeah, XP is the first NT kernel end user operating system, and that's why it has significance. Microsoft actually has extended support for Windows XP because there are so many companies out there still running it.
Mm-hmm.
They have been, threatening to discontinue support for XP for many years now. And they're still doing it because there are big companies who are basically saying, if you don't support XP, we're not going to buy Windows anymore. Basically, that's what they're saying. All right, so moving on to stealing this idea, because I'm just sick and tired of people talking about Flappy Bird. Because that's all I heard over the weekend is Flappy Bird, Flappy Bird, Flappy Bird. It's like, well, it's, and I looked at it. Somebody actually showed it to me, and I looked at it and go like, wow. Back to the 90s, cool. So I want a game that does this, okay? It would use the accelerometer of a mobile device, and you will basically be looking out, like a window or a little slit out of a turret. Okay, so you can make it a shooting game and whatnot, but it will be sensitive to your motion. So wherever you look, it's kind of like looking in that direction. I have yet to find a game like that. I think the Nintendo 3DS, has many games already making use of that particular feature. But in terms of Android or iOS devices, I haven't seen a whole lot of games that would do basically superimpose images like that for
There's
as a
a
game.
game on the Apple iTunes called the NRA, and it's they produced this game, and I have it on my iPhone.
Okay.
It's just like that. You get to pick your gun, and they shoot up like the clay pigeons.
Mhm.
You move the thing around to get the clay pigeon, then you got to tap the button.
Okay.
To shoot.
Yeah, but they can make it a game that uses augmented reality too. Now that would be cool because when you actually see people in the from the camera, it will superimpose people with zombies, right? Images of zombies. So now you'll be using a phone, you can see people on the bus doing this, right? Don't bite me.
Just walking up to you.
All right, this is the last one. Now this one is kind of really, really interesting. It has to do with the statistics. And the question is, who is not getting into computer science? Who is not getting into computer science? And if you click on this link here, it is interesting. As Californians, we don't really experience anything like this. No girls, blacks, or Hispanics take AP computer science exam in some states. The entire state does not have a single girl, female, black, or Hispanic taking these exams. So that happened to certain states. You can read the detail for the states. Mississippi, Montana, no female, African American, or Hispanic student took the advanced placement exam in computer science. Out of the entire state. I'm not talking about a certain district, okay? Even in California, I can imagine there are certain districts that may have statistics like this. But if you just look at a town, a city, probably it's not likely to find that. But these are entire states.
Wow.
So it's just kind of, sorry? Good.
I said, how many black people are in Montana?
I don't know.
How many people are in Montana?
Well, but surely it is not going to be like, it still doesn't explain these numbers. And then if you look at just sheer numbers, so this one is kind of skewed to the bigger states. This is just reflecting the number of female test takers by state. California has 4,000, close to 5,000 students, and of which 21.64 are female. Texas has about the same statistics, just a little bit more in terms of the percentage. So these are the two states with more basically female students. New York is about the same in terms of percentage. So the bubbles are really just proportional to the total number of people taking the test. But still, I think the statistics are very interesting, depending on which state we are talking about here. So just interesting facts that I want to share with you guys, and then we can now get back to the boring stuff. How do we have
I
to?
moved here from your position. And I mean, we had an influx of Hispanics after Hurricane Katrina, and I lived on the coast, so a lot of people came in to kind of work and rebuild. So we did have some Hispanics, but other than that, we didn't have very many at all. You don't see very many immigrants or minorities besides African Americans.
So mainly it's Caucasians,
Pretty much
African Americans.
There's a lot of white people and a lot of black people. Female people down there are very smart, so I can see why they don't have very many people taking the AP exams. But again, females, they said no females took the AP exams.
Yep.
I took a lot of classes in college with females, no African Americans, just white guys and females in computer science. That's kind of crazy. None of those people.
I can share with you, this is not myself, this is someone, whom I know, when I was in graduate school. So he is a Chinese American, and his strategy of picking which class to take is as follows. He would walk into a classroom and look at, the just an overall color of hair color. If overall speaking is kind of dark, he would just walk out and drop that class. what he's suggesting, I'm not going to say anything because that can be considered
It's not
racist
your
or
opinion.
whatnot.
It was his opinion. You're just telling us what his mindset was.
Yeah, that was his strategy. That he said, I'm going to take the class again. I mean,
I assume
I'm
it's
going to
because
drop
like
this.
Asian people and a couple other ethnicities mainly have black or
Darker.
really dark hair color,
Mhm.
and so if it's graded on a curve, and he was probably basing it on the stereotype that Asians are really good at
That
that.
probably was his reasoning. Yep.
If I had to take a shot at it.
And this was Davis, okay? This was just Davis. Imagine what would happen when you go to Berkeley.
He probably wouldn't be taking any classes.
No, Berkeley is far more competitive compared to Davis. Yeah, I have heard horror stories from Berkeley, where people would break into lockers to sabotage other people's projects.
Yeah.
So I'm not just talking about, oh, you want to ask me a question about something, you want me to help you, I'm not going to help you, because if I help you, you might end up with a better score than I am and bump me down the grade. Okay, that's just passively trying to defend your own grade, okay, which is not nice to begin with.
At least you're insulting the
We are
audience.
talking about actively going into somebody else's project and sabotage it, so
Wow.
to basically improve your ranking in class. I mean, improve the ranking of that
Because
student
they
in
can't
class.
do it academically.
Well, I think that's really competition gone wrong. I mean, it's definitely questionable.
Yeah.
All right. Well, good thing we don't have a grading by curve in this class. All right. So let's go ahead and go back to the previous homework assignment. I will give you the solution first, and then we'll go ahead and continue with the next homework assignment. Is Mark Twain from Mississippi? Is he a native of Mississippi as a state?
Yeah.
And he is a smart man. I mean, his quotes. There are many quotes from Mark Twain that are truly, smart.
It's too bad they're censoring his books. For the originality. It's
Oprah.
the Oprah.
Oprah, Brett Favre.
Oh, yeah, it's ruining. Well,
Even Star Trek: The Next Generation had quite a few episodes with Mark Twain in it. Yep. All right, so let's get back to this one. So we want to figure out what is happening to all the variables as we run through this algorithm. We start with line 1, and on line 1 we have a regular homework. Not homework, but regular assignment statement. The right-hand side is just a constant of 5, so the value of the right-hand side is just 5. We copy that to the variable specified on the left-hand side, which is x. So x gets updated to a value of 5. Y is not changed, so we get to retain the value of question mark. Now, if you want to use the new shorthand and not to do anything, not to mark anything when nothing is being changed, you can just leave it blank. Okay, so that's perfectly okay as well. Moving on to the next line. Line 2. Well, line 2 is fairly simple. Nothing happens to x, so x gets to retain its value of 5. Y, on the other hand, is updated by the right-hand side. The right-hand side is 2, so y is now updated to a value of 2. So I would imagine the first 2 lines should not pose any problems at all. Line 3 is a little bit more tricky. Nothing happens to x, so x still gets its own value of 5. But y it can be confusing because we have y on the left-hand side and y on the right-hand side. But remember the ordering of doing things with an assignment statement. We evaluate the right-hand side first. Okay? So when we evaluate the right-hand side, which is y plus y, what is the current value of y at this point? 2. 2 plus 2 is 4. So the entire right-hand side evaluates to a value of 4. And what do we do with that value of 4? So we use it to update the left-hand side, which is also y. Okay, so y is now doubled to a value of 4. And then we move on to line 4. Line 4 does not affect y. Y gets to retain its value of 4. X is the one that is affected. But before we try to figure out how it's affected, let's evaluate the right-hand side first. The right-hand side specifies x plus y. X currently has a value of 5. Y currently has a value of 4. 5 plus 4 is 9. So 9 is the value that we use to update X. So X is now updated to a value of 9. And that's the last line of this entire program. We use post to indicate we are now at the end. So we're done.
If for pre, I put 0, is that wrong?
That would be wrong because I think the question marks were in the trace to begin with, so you should not change that to a 0. But that's going to be a minor point to take about, not major. Are there any questions about this trace? No questions about the trace? This is all good? Okay. So let me move on then. And I'm kind of surprised that nobody is reminding me of the one thing that I wrote on the whiteboard. I wrote it on the whiteboard, so that you guys can remind me to talk about it, because I usually don't look back and see what's on the whiteboard. Okay, so we want to talk a little bit about this because I think at least 2 people asked me from this class what classes to take and so on and so forth. So I'm going to give you a little map here. Okay, this is cisp 300. We're currently in cisp 300, which feeds into cisp 360. So I would imagine the majority of people in this class will take cisp 360 because it's not just applicable to computer science students, it is also applicable to engineering, math, and other types of students. But from there on, then it depends on your major. If your major is computer science or you're trying to get a computer science transfer degree, then the next class after 360, there are actually multiple classes after this. The first one is cisp 400, which is object-oriented programming in C++. The other one you can take right away is cisp 310, which is assembly language programming. Okay. Now, out of 400, you can also take cisp 430 and also cisp 440. I believe cisp 440 has a co-requisite of cisp 430, so these two are usually taken in the same semester. Am I leaving any classes out? No, I think these are all the computer science classes in the computer science transfer degree. Are there any questions about this picture? Yep.
So you take 310 before you can take 400?
No, these two can be taken in the same semester, if they are offered in the same semester. But they're both kind of heavy-duty programming classes, so depending on your load with your other classes, work situation, and other things, this is a 4-unit class, this is also a 4-unit class, and they're both kind of heavy-duty programming classes. So you have to allocate resources accordingly. Okay, any other questions? So if you want to ask, which ones are your programming classes, this one is heavily, it's definitely a programming class where you'll be writing programs. This one too, and this one kind of, and this one is not. This is basically a math class where you really do not have to write programs. So are there any questions about this? No questions? Yep.
You said that's for computer science only. If you go into engineering, does it vary depending on?
If you go into engineering, you have to look at the engineering transfer degree. If it's not in place right now, it should be in place soon. I would imagine you're taking some classes from our own engineering department here. So you might want to ask those professors, about the sequencing of classes. What they're trying to do is they're trying to standardize everything. So if you want to transfer to a computer science program in a CSU or a UC, the CS computer science transfer degree will do it. And it's regardless of which school. Okay, so it applies to UC Irvine, it applies to UC Davis, it applies to Chico, CSU, Chico, and so on. So it doesn't matter which school. And they're doing exactly the same thing across all the disciplines. So engineering is one of those, they also have their own transfer degree. So we can look it up. So this applies to math majors too. So if anyone here, is not in engineering or computer science, you can also look it up, for your own major. So we can look up engineering transfer degree, and just add CID to it, course ID, and we should find something here. Course ID .net course identification. We want to look for engineering to be specific. There's no engineering. There's computer science. Doesn't look like. Which engineering are you? Electrical? I don't see anything related to that. There's math here. So if you look at the math program, why does it need my Google account? Oh, okay, I see. It's just okay, so if you're a math major, it will kind of outline what classes you need to take. So there are 3 math classes, physics, and it doesn't list any computer science classes anymore. Yep.
When I went to the counselor for electrical engineering and transferred to UC San Diego, it said, not specifically, it just kind of said, must take most rigorous computer programming class.
Okay.
What do you think that would mean?
Well, in that case, I would go to assist.org and see if you can find more information there. So this is a really good resource as well. It's called assist.org. So what you do is you look up, American River College, assuming you're going to get your degree here, and then you look for the other campus. So in your case, it's UCSD. So we look up University of California, San Diego. And then you can pick either by a major over there or a major over here. So let's look up a major over there. And you said electrical engineering?
Yeah.
Okay, so we go to electrical and computer engineering. And this is their list. This is the articulation agreement between the 2 campuses. In other words, if you take, no course articulated, great. So for whatever reason, they have not articulated any courses with us over here. So that means you really have to contact the people over there and ask them which class you take here can be counted as classes over there. But if you go back to other UC
major. Go to the one above by major.
By major? Okay, let's give that a try. So we want to go by electrical ECE, electrical engineering BS. Yeah, it's still not showing anything. It's just general advice. So that's what your counselor is telling you. It's because even in assist, they only mention a recommended list. General advice: transfer students are advised to complete the following for their major before enrolling. Preparing well for the major helps students move efficiently toward graduation. But it has no promises whatsoever that these classes that you take here will be counted as equivalent classes over there. It's just saying, it might.
Maybe they have a test that you take when you get there, just see where you are.
It doesn't say anything. It has no mentioning whatsoever. But it does say highest level of C programming language course offered at the community college. So here, it really depends on how you look at this chart here, because if you look at this, this is definitely using C++, but it's an introduction class. It's kind of like going through the topics that we go over in this class, but specific to C++. In cisp300, it is also using C++, but using it in an object-oriented way, so they focus more on the object-oriented design portion. cisp330 is data structure, and once again, it is also using C++, but it's using C++ to talk about data structure. So if you look at this picture, what they mention over there can be referring to this class. But most colleges will only be referring to this one, or even just this one here. So you kind of have to contact San Diego and ask someone in their department or look through their program and see how far they go within their own program. Do they really have to go all the way to data structure, or do they stop at object-oriented programming, or even before that? Does that answer your question? Okay. Yeah, but with other UCs and CSUs, this list is more specific. Any other questions related to what classes to take? Yep, go ahead.
Like you said, you listed out the math, but I looked it up. There's other classes like CSC 15, CSC 20, 28, etc. Would those classes be available here, or I don't know what classes?
It depends on the title. I'm not familiar with the titles.
Oh, it's like Program Concept Method 1 or 2 or Discrete Structures for Computer Science, Introduction to Computer.
This is discrete structure. 440 is discrete structure.
There's like Introduction to Systems Programming and Unix, etc.
That one we used to offer, but we do not offer that class anymore because when we did offer that class, enrollment tends to be low. But that's before we have the in-search of computer science students. So there might be a chance that we might restart that class too.
So, for example, the ones that you listed are mostly the prereqs if you wanted to transfer out.
This will complete your computer science transfer degree. So it also depends on by the time you complete all your classes here, whether the computer science transfer degree will be implemented throughout the entire state. So there's a lot of unknown at this point. When are we going to transition from a cis.org, which is a campus-to-campus type of articulation, to a statewide articulation using the transfer degree? So there's a lot of unknown at this point. The timeline is not really published. So we don't know how soon they can move on to the statewide system.
All right, thank you.
But your counselor may know more of the deadline. The timeline of this whole thing, but I don't know the timeline. Right. So I'm hoping that this picture helps out, your planning of what classes to take next and which semester you should be taking which class. We are also going to offer these classes a little bit more frequently. For instance, CISP 310 used to be offered only every spring. So if you miss spring, you will have to wait a year to take it. But now we are starting to offer CISP 310 every semester. The reason is simple because this semester I have 65 students in CISP 310. The healthy class size for CISP 310 would be about 25 to 28. It's a little bit less than this class because that class is kind of heavy-duty programming class. The concepts are more difficult to explain and stuff like that. And now I have 65 students, more than twice the recommended number of students in the class. But if they don't take it this semester, they will have to wait another year to take it if we don't offer that every semester. So that's why we are starting to offer many of these classes every semester. But at the same time, we have 5 sections of CISP 300. So you might still end up with a situation where you cannot get into a class to move on, with the program. All right, so that's that. I'm going to close this one, and we can now move on to the next homework assignment. So I will talk about the homework assignment first, and then we'll go over the concepts that you need for the homework assignment. So the new homework assignment is called a while statement, and in it we will take a look at what a while statement looks like. All right, so here we have your next homework assignment due in 1 week. Okay, so this one you have 7 days to do it as well. And this is what we'll talk about today. Okay, we'll talk about this concept today so that you will be able to do the homework assignment. All right, so I'm going to leave this one up, on the projector or on my desktop for the time being. And we'll go back and finish up conditional statements first. Right, so with conditional statements, we are already done with logical operators. We talked about the words and, or, not. Those are logical operators. The only thing that we have not really finished is basically how do we use else-if statements. So instead of just looking at the notes here, we're going to complete the algorithm in an incorrect way, and then we'll try to spot problems with that algorithm. This is from last class, so it's okay to kind of reuse the same notes here. So if you look at this code here, it is the logic to find the maximum of 3 variables, and then use z to keep track of the maximum of these 3 variables. In other words, you are given the values of w, x, and y, 3 variables input, and you need to find out what is the maximum of those 3 values and store the maximum in variable z. That would be the job of this algorithm. And I can tell you right away that there's a problem with this algorithm. It is not entirely correct. Okay? So as we trace this algorithm, we'll go ahead and figure out what is wrong with it, and then we'll raise the question of how can we ever be sure that an algorithm is actually correct. So we'll keep this one up, and we'll go ahead and trace it right now. Starting with a spreadsheet. If w is greater than x and w is greater than y, then z gets w because w is the maximum. Else if x is greater than w and x is greater than y, then x is the maximum, so z gets the value of x. Else, if w and x are not the maximum, then z is going to get the value of the 3rd variable, which is y, and if. So on the surface, this logic seems to work. I mean, it seems to be fairly logical, and it should get the job done. Should not have any problems. So what we'll do is we'll trace this algorithm a few times, just to see how it works. But as we do this, we will also spot problems with the algorithm. We'll have 3 test cases that work correctly and then 1 that does not work correctly. Because it has conditional statements, we need a column labeled comments so that we can keep track of the value of the expressions. And then we have our usual line number. We have 3 variables in this case, w, x, y, and 1 as the output, which is z. So we technically have 4 variables. So it's going to be z. And I'll go ahead and make these columns a little bit smaller because they really don't need to be that wide. And line number can be a little bit shorter too. Column should be, comments should be okay here. Okay, so this is our first test case. In the first test case, let me give you specific values of w, x, and y first, and then we can determine what the algorithm is going to do. This is one of the many cases that I will give you initial values for the variables, because otherwise we cannot trace it. We cannot say, okay, w is greater than x, is it true or is it false? Well, if w is a question mark and x is a question mark, we cannot evaluate the comparison. So in this case, I'm going to give you some initial values. Don't ask me why those are the values. It is just given to you as a test case. All right. Do we have any questions at this point? How to set up the trace at this point? Okay, if there are no questions, we'll go ahead and trace it. On line 1, we have to evaluate the condition. The condition in this case is a conjunction because it has the word and in it. So we have to evaluate w is greater than x as well as w is greater than y. W is greater than x is true. W is greater than y is true. So we have true and true. According to the definition of conjunction, what is true and true? True is true. Okay, very good. So the entire expression is true. And then where do we go?
Line 2.
We go to line 2. Okay, very good. Because line 2 is the branch or the action associated with the condition on line 1. So when that condition is true, we perform the action specified on line 2. All right, so we move on to line 2. Line 2 is a regular assignment statement, which means we copy the right-hand side to the left-hand side. The right-hand side specifies w as an expression. W currently has a value of 3, so we update z to have the same value. And then where do we go? It's a conditional statement. Post, very good. Okay, that is the correct answer. We get to post right away because with a multi-branch conditional statement, it is still a conditional statement. If you take one branch, then you get out after that branch is finished. Okay. All right, so let's move on to the next test case. So this one works fine. Did the algorithm work correctly? In other words, is 3 the maximum of 3, 1, and 2?
Yes.
That is correct. Okay, so it works out just fine. All right, so let's go ahead and create the next test case. So in the next test case, I'm going to kind of change things around a little bit here. I'm just going to exchange the values between W and X and see if the algorithm is going to work correctly again this time. On line 1, we have W is greater than X. W is greater than X is false. Okay. And what about W is greater than Y? It's also false. So we have false and false. What is false and false?
False.
Is false. Okay. In order for conjunction to be true, you need both sides to be true for the entire thing to be true. So now we move on to where? The condition of line 1 is false. We read the program top to bottom. So what do you think is the next line we have to execute? Line 3. Okay. We skip line 2 because line 2 is the branch corresponding to a condition that is false. On line 3, we have a different condition to evaluate. We have X is greater than W, which is true. We have X is greater than Y, which is true. True and true is true. So the entire expression is true. So we perform the action specified next to the condition, which is on line 4. Line 4 copies the value of X to Z. X has a value of 3. Z ends up with a value of 3 as well. And then what do? Post. Post. Exactly. We are now done with this multi-branch conditional statement. We take one branch, we get through the entire branch, and then we get out of the conditional statement. All right, so let's go ahead and work on the third test case that is still going to work correctly. Okay. So we'll erase this portion, and this time I'll exchange the values between X and Y. So X ends up with the value of 2, Y ends up with the value of 3. So let's figure out what is going to happen this time. On line 1, W is greater than X is false. W is greater than Y is false, right? Because the 1 is greater than 3 is false. So the entire thing is false because both sides of the conjunction is false. So the entire conjunction is false. We go to line 3 because we read the program from top to bottom. On line 3, we have a different condition to evaluate. X is greater than W is true. X is greater than Y is false. True and false is false. So we cannot execute line 4 as a result. So now we have to go to line 6 because line 6 is a catch-all type of branch. If all the previous conditions are false, then we get to line 6, which is just an else statement. On line 6, we copy the value of Y to Z. Y has a value of 3, so Z now ends up with a value of 3. And we are done with this one. We get to post. So in this case, it seems to be doing the right thing too. I mean, Z is the maximum, and the maximum of 1, 2, and 3 certainly is 3. So far, the algorithm has not shown us anything that is incorrect. Does that mean the algorithm is correct? Nope. Okay, it only takes one counterexample to prove something is wrong. Right, so in the fourth test case, we will try to break the algorithm. In other words, we'll try to make it do something that is incorrect. All right, so can someone make a suggestion how to make this program work incorrectly? The end result is incorrect. Okay, which two?
Say W and X.
W and X?
Yeah.
Okay. It has to do with which two, because if you make Y one of the maximums, then it's not going to be, the output is not going to be flawed.
Okay.
Yep. So let's make W and X both being the maximum of the 3. So I can make that happen just by changing W to 4 and X to 4 as well. Okay. So let's find out what's going to happen in this case. On line 1, we have W is greater than X. That's false already, okay? But just to be sure, I will also evaluate the other side. W is greater than Y is true. We have false and true. false and true is false. Then we move on to line 3. Because the condition is false, we want to see if the next condition is true or false. The next one is x is greater than w. Is that true or false?
False.
That's false. And then we have x is greater than y, which is
True.
true. False and true is
False.
false. Okay. And so we now have no choice but to go to the catch-all case on line 6. Line 6 is going to copy the value of y to z. Z ends up with a value of 3. We get to post, and this time we have the wrong answer because the maximum of 4, 4, and 3 should be 4 and not 3. So are we doing okay so far with this pseudocode at this point? You know, just understanding that it is not always correct. Okay. I think last time we also used this analogy. So just kind of imagine. Okay, I'm going to draw this picture again so I can more easily explain what this is about. Okay, so kind of imagine that the black dots here are cases where an algorithm is going to give you the incorrect output, incorrect result. Okay, so these are black dots. But on top of the black dots on the whiteboard, I'm going to use a big disk, a blue disk, solid color, opaque, to cover up the black dots. Okay? The blue disk is representing all the possible inputs pattern to this particular algorithm. The black dots are representing the incorrect case, or the cases where the algorithm will not give you the correct result. So when you're testing an algorithm, you can only see the blue portion. Because if you knew that the black dots were here, you would not have to test it. You can just say, oh, the algorithm is incorrect. So what you're doing is you're throwing darts randomly at the blue disk. And then you pull the dart out and go, okay, is there a black dot behind this? Okay, if there's a black dot behind it, then you know the algorithm has a problem. If there's no black dot behind it, then the algorithm is correct for that particular test case. So the question now is, how many darts do you have to throw in order for one dart to land on the black dot so that you can realize the algorithm is not entirely correct? That is the question. It depends, okay? It all depends. If you're talking about an algorithm that finds the maximum of 2 variables, it's not too bad. It really is not too bad. There are ways you can enumerate and test every possible case in that case. 3 variables, it's getting more complicated, okay, because there are more test cases now. So when you are working on a real algorithm, a lot of times it is not possible because your disk, the blue disk, is so huge that it is impractical to throw darts at every single possible location. But yet, if you just throw a few darts and they all not land on the black dot, it is no proof at all that the algorithm is correct either. So here's the big question. How can we check and verify that an algorithm is correct for all possible cases? So that really is a question. I cannot answer that question today because it's not the time to do that yet. However, there are techniques to use mathematical proof, step by step, to prove that an algorithm is correct for all possible input cases. In other words, I can prove an algorithm like this one, okay, that it is either correct or incorrect without throwing a single test case at it. And just by using mathematics, I can prove that it is correct or incorrect. Okay. So that is something that we are going to do too in this class, just a little bit, later on, not right now. So what we are going to do right now is to kind of wrap up conditional statements. So I will going to give you this picture here. If you compare this picture with the algorithm that we just experimented with, they are both representing exactly the same logic. Yep.
Roll sheet.
Roll sheet. Thank you. So these two, one is a picture and the other one is pseudocode, but they represent exactly the same logic. In other words, when you have a multi-branch conditional statement, the way you do it is you have ordering of the conditions. You read the multi-branch conditional statement from top to bottom, just like with any other algorithm. So in this case, the condition w is greater than x and w is greater than y is the first condition to evaluate. If that condition evaluates to true, then you take the branch, which is line 2, associated with that condition, and then after that you exit the entire multi-branch conditional statement. If the condition on line 1 is false, then you follow the false path, and then you have a second condition to evaluate in this case, because line 3 gives you a second chance to evaluate another condition. If that condition, the second condition, evaluates to true, then you execute the statement on line 4, and then you get out of the entire conditional statement. If that condition evaluates to false, then you follow the other path, which is on line 6 here, and then you exit the entire path. So are there any questions corresponding the pseudocode on the right-hand side to the picture or the pictorial representation on the left-hand side? Yep.
What do you mean by maximum?
Maximum means, if you have several numbers, which number is the largest? The largest number out of those few numbers would be the maximum. You can have non-unique maximum. So in other words, if I give you 3 numbers, 16, 16, and 16, then 16 as a value is both the maximum and the minimum of the 3 because you don't have any variation within the 3 numbers. All right, so what we'll do is I'm going to suspend the discussion of multi-branch conditional statements here. We'll go through some tricky cases later on, but for now we're going to move on to talk about loops. So I'm going to change the order of discussion a little bit and start with loops first, just so that we can do the homework assignment. So with loops, we'll start with a while loop because that's the one that we have in the homework assignment. And instead of giving you the line-by-line trace, I'm going to give you the picture first. This is what a pre-checking loop looks like in terms of a trail path. The way it works is you walk in from the north, okay, going down. The first thing you encounter is this sign here. It is a condition. This condition is, well, I use eating as an example. So this is the condition to evaluate. If the condition evaluates to a value of true, we follow this path here. We perform the action specified in the loop between the while and the end while. And after we perform the action, you can see that this path goes all the way back to the beginning right before we evaluate the condition. So you have to re-evaluate the condition after the first iteration to see whether it is time to exit or whether you want to perform another iteration. So you keep doing this loop here again and again until one time you come back here, this condition evaluates to false, then you follow the path that is labeled false and you go all the way out of the loop in this case. It is called a pre-checking loop because we check the condition before we perform the action. Are there any questions about the general concept displayed in this picture? No questions? Okay. So let's go ahead and do, let's trace one algorithm that has a pre-checking loop. And we have a few to pick from. I'm not going to trace this one because that's your homework. So what we'll do is we'll trace, something else. So let's go ahead and make another trace, another algorithm using a pre-checking loop. And I have to really think hard not to make it resemble your homework assignment. So let's try. Let's try this. Okay, x is initialized to 81 to begin with, and it will say while x is not 3, do the following. And what we'll do in the loop here is x gets x divided by 3, and while. Okay. This is my entire algorithm. And I want to find out what it's going to do. We'll trace it in sheet 2. because we have a condition to evaluate, and because the condition helps determine which way to go in case of a branch, we need a column comments. We need a comments column in order to document that. And then we have our usual line number and a single column for our variable x. So, and then I can give you a precondition. If I give you a specific value for x, do you think that would be useful at all in this algorithm?
Yes, initialize that here. Well,
Nope.
no.
It's not going to be helpful because
It already initializes on step 1.
on line 1 I'm going to overwrite it, right? So even if I say that, let's say x starts with a value of 16, okay, is it going to be helpful? No, because on line 1 I'm going to overwrite the value of x right away, so it doesn't matter if I give you a particular value in the precondition in this case. So we might as well just say that we don't need to know the initial value of x because the algorithm is going to initialize it anyway. So that's exactly what line 1 is going to do. It will initialize the value of x to 81. So x is now 81. We move on to line 2. X is not 3 is true. It's true because 81 does not equal to 3. And once again, the less than greater than symbol means not equal to. And where do we go? If the condition of a pre-checking loop is true, where do we go? Do we get out of the loop or do we get into the body of the loop between the while and the end while?
Into the body.
Into the body, because if we go take a look at the picture, the path labeled true is to go into the action of the loop and not to get out of the loop. So that's why we have to do the same thing when we do the trace. So we move on to line 3. Line 3 is an assignment statement, and this is how we represent division in a program. And it has to do with the normal division symbol, which is a dot, a bar, and a dot, is not on the keyboard. So that makes it kind of hard to type. And programmers just find that, hey, there's a slash symbol. We can use the slash symbol to represent division. And that's how most programming languages use for division. So the /3 means divided by 3. The right-hand side is x divided by 3. X is 81. What is 81 divided by 3? 27. And this is an assignment statement. The left-hand side specifies x here. So that means variable x is going to be updated by the value 27. And so we have 27 here. And then what do we do? Well, let's take a look at the picture again. After we perform the action specified between the while and the end while, what are we supposed to do? Go back to reevaluate the condition, which is line 2 in our case. So we're going to go back to line 2 and reevaluate the condition. X is not 3 is true. It is still true because 27 does not equal to 3 is true. Okay, so it is still true, so that means we have to go back to line 3. This time we have 27 divided by 3, which is 9, and then we update x with the value. X now ends up with a value of 9. We go back to line 2. X is not 3. It's still true because 9 is not 3. We go to line 3. 9 divided by 3 is 3. And then we go back to line 2. X does not equal to 3 is false. It's false because x equals 3 is true, but x is different from 3 is false. So when the condition is false, according to the picture, we are going to take this other branch and get out of the loop entirely. So that's exactly what we're going to do here. We get the post. Now, with this particular trace, there are a few places where people can make mistakes, and I will count it. I will deduct points for those mistakes. The first one is to move the post all the way up here. You cannot go from line 3 to post, because line 3 has no way to make a decision. Line 3 is just there and say, when I'm done, I'm going to go back to the beginning of the loop. So you cannot go from line 3 to post directly. You can only get to post through line 2, because line 2 is the only line in this entire program to make a decision. Should I perform another iteration, or should I get out of the loop and get to the end of the entire program? So that's why line 2 is mandatory. It has to be here. And then the other lines, it has to alternate between line 2 and line 3. In other words, you cannot combine line 2 and 3 and just say, oh, here's the condition, and X gets updated here. Cannot be combined into one single line, because one line, line 2, is responsible of making the decision, should I exit or should I go for another iteration? The job of line 3 is to update the value of X, and that's why they cannot be combined into a single line in the trace, because they are distinct steps. 2 different steps to perform. Are there any questions about the convention of tracing a loop like this? If
For
there are no
those,
questions,
for
yep.
lines like 5, 7, and 9, if we inputted line 3, like the X is, would that have been wrong to do, or like
Oh,
how
you
you
fill it in?
on the left side you have line 3. Now we go to the right side where we have lines 5, 7, and 9, where line 3 would go. If we were to add those comments in, would that be considered wrong, or
The division part.
yeah,
No.
like actually just adding the division in, just
Oh,
using
you can-
the lines,
no,
you can-
so you know what's going on.
You can add additional stuff to the comments column, and that's what it's for. It's really just for commenting. But this is the minimum that I'm expecting, because I need to know why are you continuing onto line 3 on row 4. Okay, if you look at row 4 of the trace, I need some justification of why are we continuing on line 3 instead of post. And that's exactly the explanation that I need, is to say, oh, but the condition is true, so that's why we are not exiting the loop. So looking at this, and let me just kind of go back to your homework assignment. Do you think you can do your homework assignment given the trace that I have given you already?
Yes.
Okay, excellent. It's more about convention, how do we trace something, than the actual logic. I think you guys are getting the logic anyway. It's just that this is the convention that I'm expecting out of your answers. All right, so this is all done. Very good. And now we go back to multi-branch conditional statements, and I'm going to throw some curveballs at you, okay, and see whether you guys can tell me what's going to happen when a particular algorithm executes. All right, so we'll go ahead, I'm going to use a different case compared to the previous class here. So I'm going to say, if X is greater than 1,000, then Z gets a value of 1. Else, if X is less than 0, then Z gets a value of 2. And then we say else if X is greater than 2,000, then Z gets a value of 3. Else if X is less than or equal to 1,000, and Z gets a value of 4, else Z gets a value of 5, and if. I'm going to explain why we need indentation later. When we get to nested statements, then it'll be clear why the indentation is important. At this point, you can just kind of say, well, it's just there so that things are a little bit easier to read. All right, so here we have a multi-branch conditional statement that has quite a few branches. Okay, we have 5 branches altogether. The way I count the 5 branches is 1, 2, 3, 4, 5. So there are 5 ways to branch in this particular multi-branch conditional statement. I did not bother to redraw this picture, but that's basically what it looks like. The first decision point is line 1. X is greater than 1,000. Is it true or is it false? The second point of decision making is line 3. X is less than 0. Is it true or is it false? The third point of decision making is line 5, which is X is greater than 2,000. Is it true or is it false? And the last one, the last decision point is line 7, which is X is less than or equal to 1,000. Is it true or is it false? So if you look at it that way, this block here corresponds to line 2, 4, 6, 8, and 10. So are we okay, with the representation of the logic in pseudocode as well as a picture? Okay. So keep that in mind as we trace it. Okay. I'm going to give you a few test cases in this case. So once again, because we have conditions to evaluate, we need to have the comments column, line number, X and Z. The variables are not really that important. It really is just there to facilitate the execution of the algorithm and to trace what is happening as we go through the algorithm. All right, so the precondition, as for the precondition here, I need to give you a particular value for X because the first thing we do to X is not to override it with something else, but to read the value. Okay, so I need to give you a particular value in order to trace this algorithm. Let's start with something simple. Okay, so I'm going to start with, let's try 3,000. Oh, that's actually not as simple as I thought. Let me try it with something else. -1 is 1, and then Z can start with an unknown value because all 5 branches will overwrite the value of Z, so it doesn't need to start with a particular value. Okay, so we look at line 1. Line 1, the condition on line 1 is X is greater than 1,000. Is it true or is it false?
It's false.
Okay. So we move on to line 3 because we read from top to bottom. If one condition fails, we move on to the next available one, and then we keep going until there's none left. Okay, on line 3, the condition is X is less than 0. Is it true or is it false?
True.
It is true, and then what do we do? We perform, where do we go next?
4.
We go to line 4, which is the action associated with the condition of line 3. Z gets updated to a value of 2, and then where do we go? Post, exactly. If you look at the picture, anytime you take one branch, it doesn't matter which one, lines 2, 4, 6, 8, or 10. If you take one particular branch, when you're done with that branch, you go all the way to the end of the statement. So that's okay. Well, I kind of lied. This is already a somewhat complicated case. There's actually no simple case in this case, in this algorithm. What about line 7? X is less than or equal to 1,000. I mean, surely -1 is less than or equal to 1,000. How come we don't go there?
Because we already accessed what it's supposed to be. Granted a previous statement.
It's top to bottom for one thing, but we already took that one branch. In other words, in this particular case, we start with line 1. We say, oh, X is greater than 1,000 is false. So we follow the branch to here. Now here we are on line 3. X is less than 0. Is it true or false? It is true. So we follow this logic. We end up here, which gives the value of 2 to Z. But what do we do after this branch? According to this, we don't go back here and continue with all the other conditions. We continue all the way to the end of the multi-branch conditional statement. And that's why line 7 is not even considered in this case, because we took one branch already before we got to line 7. Are we doing okay so far with that logic? In other words, to be more clear, all of these arrows are in one direction only. There's no way to go back up and say, hey, I want to evaluate the other conditions too. No, if one is true, you take that branch, you do not go back up to re-evaluate other conditions.
It's like the first conditions take priority over the later conditions.
Yes, because of the way we read the algorithm. Because we read the algorithm from top to bottom, so that's why we always evaluate in that order. Which also means if I change the ordering, it will change the behavior of the algorithm. All right, so this is one test branch. We'll test something else. But I think you guys are getting it, so it is okay to feel bored. Feeling bored in this sense, is good because you're basically saying, I know what it's going to do already, okay? So let's try, 2001, okay? So this is the kind of things that I might do in a test, is to give you values that are kind of misleading. Now the way it is misleading is because when you just kind of glance through the algorithm and you compare the value of X, a lot of people will instantly go to line 5, right? 2000, 2001, hey, that's a, they would just kind of skip all the other lines. Well, but if you are taking this class, you cannot do that, okay? Because the computer is not going to glance through the algorithm and say, hey, 2000 is related to 2001. I'm going to skip all the way to line 5 and start with that. Nope. The computer does not do that. It always starts with line 1 and then go from top to bottom. And that's exactly what we need to do here, is to start with line 1. Line 1 is saying x is greater than 1000. Is it true or is it false?
True.
True. It is true right away. We go to line 2. Z gets a value of 1. We took one branch, and we finish that branch, and we are now done. That's it. But x is greater than 2000. Yes, it is, but we don't get there. Okay. So following this logic, don't you think in this code here that some of these branches have a problem, like we can never get there?
Yeah.
Which branch do you think we cannot get to?
5.
Okay, this branch here we cannot get to. I think there's one more branch that we cannot get to. Yeah, I'll take it. Yep, there's another branch we cannot get to.
5.
This branch we cannot get to either.
Right.
Anything that's greater than 1000.
Yep, because anything, the other way around, anything that's greater than 2000 is automatically greater than 1000. But because we checked for greater than 1000 first, it will catch values of 2001, 2002, which is just what we did. So this is what we call a dead branch. In other words, it's not a syntax problem. It is not going to cause the program to crash. But even though the code is specified on line 6, it would never execute. There's no way to get to line 6, no matter what value you put into x. Is that making any sense? Now, dead branches they're not quote-unquote harmful in a way, because it's not going to cause the program to crash. But at the same time, they're also kind of problematic, because people put this line in because they think it will execute at some point, because otherwise they would not put that code in at all. And yet, because of the arrangement of the conditions and the ordering of the comparison, we actually never get to line 6. So this is kind of a notorious kind of bug, because it's not going to cause the program to crash most of the time. It is there syntactically, it looks good, it looks right. And yet it is causing a problem because this branch will never execute, even though some people or the original programmer may think that this line will get executed at some time. It doesn't get executed at all. So that's why when you write multi-branch conditional statement, you kind of have to keep in mind, of the ordering of the conditions, and double check and make sure that it catch all the cases that you need to catch. You need to think about the perspective, from the perspective of each branch, and say, okay, when is line 6 going to execute? Okay, you need to think about your algorithm from that perspective. Are there any questions about this algorithm at this point? What about line 10? Line 10 is also a dead branch, because between line 1 and line 7, it would have caught all the possible cases. Because a number can either be greater than 1000 or less than or equal to 1000. There are no other ways. So between these two, we know that all cases will be caught already. And that's why there's no way we can fall through to the else case here. All right. Are there any questions about this algorithm and why multi-branch conditional statements can be tricky? No questions? This is all good. I just realized one thing. We have been talking about if this happens, then we're going to do that, and so on and so forth. And we even have conditional statements using the word if and else. And then all this time, or most of the time, I will tell you that we were using the word if incorrectly. Okay? So I'm going to give you, well, we may not have enough time to finish this, but I will get started anyway. I'm going to get started with this one. We'll probably have to finish this on Thursday. So what I'm going to do is I'll give you, I'm going to delete this. We don't need to keep this around. So I'm going to give you these three things. Okay, if, only if, and then we have if and only if. Okay, so these are the three combinations, okay, to use the word if in a sentence, but they mean different things. So let's go ahead and use an example for each one. Okay, so we'll say, if the sky is orange, everyone will fail cisp 300. Okay. Well, okay. So let's also put more stake into this. Okay. So let's say you guys pay me $50 and say give me a truth, give me a statement that is true. Okay. And I gave you this. If the sky is orange, everybody will fail cisp 300. You go like, really? I paid $50 for that? Well, it's still better than $95,000 for an iPod 5 with Flappy Bird installed, right? And I give you my money back warranty. If you can prove me wrong, you can get your $50 back plus $10. Okay, I'll give you $60 back if you can prove me wrong. Okay, is that okay so far? So that's the name of the game. And over time I would use if I would use the first one is if, the second one is only if, and then the last one is if and only if, which we also abbreviate as IFF, okay, for if and only if. All right, but the three statements are different. In other words, under different circumstances, you can get your money back. Okay, so what possibly can happen when I make this statement? What combination of things can happen? Well, let's just say that you walk outside, the sky is orange. At the end of the semester, I failed everybody. So the question now is, can you get your refund?
Okay.
Nope, because everything just kind of happened as I told you, would happen. If the sky is orange, everybody's going to fail cisp 300. So as a whole, the statement is true. Okay, this entire statement is true. You cannot get your money back. And then we'll test the second case. The sky is orange. At the end of the semester, 85% of the class passed the class. Can you get your money back in that case?
Yeah.
Yeah, because I said that if the sky is orange, everyone will fail the class. But yet 85% of the students pass the class. Well, you can get your $60 because my statement turns out to be false. So I think these two are not really difficult cases to comprehend, okay, because that's how we would interpret the word if. The problem has to do with what if the sky is not orange, okay? So for the entire semester, every single time we walk outside, the sky is either blue or overcast like today, and as it turned out, everybody failed the class. Can you get your money back? The statement is using if, okay? You cannot. Why not? Because I didn't say that the sky being orange is the only reason why everybody can fail the class. Because I could have mistakenly given you the test of CISP 430 for this class at the end of the semester. So everybody flunked the test and failed the class. And obviously you will all be lining up in front of the dean's office at a time. The dean will get an earful of what happened, right? But nonetheless, you cannot get your $60 back because the statement is still true, right? And what if I have the sky being orange is false and everybody failing the class is also false? Can you get your money back in that case? Nope, you cannot get your money back because what I said is still true. You cannot prove me wrong in that case. Now, what this really is saying is when you use the word if as the first part of this compound sentence here, you cannot get your money back if the first condition is not met. Because I didn't say a single thing about what if the sky is not orange. Okay? I did not state any truth whatsoever of what happens when the sky is not orange. My statement is specific to what if the sky is orange. The other way to look at this, which I think is less confusing, is in this case you can say the sky is orange is a sufficient condition for everyone failing the class. That is one way to look at it. Because if you look at it this way, it simply means that the sky is orange is by itself a sufficient condition for everybody to fail the class. But did I say it is the only condition? No. Did I say it is a necessary condition for everyone to fail the class? No. Not studying certainly is one reason that someone can fail the class, right? So the sky being orange is not the only reason why someone can fail the class. We are running out of time today, but as an exercise, what you can do is to substitute this if with the other two options. Substitute it with only if, and then if and only if, and see if you can just kind of figure out the meaning of the sentence, once you switch the words. Let me turn on the recorder first.